Testing, 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 testing. Hello, 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 hello. Hello, hello. Okay. Hello, hello. Okay. Okay, well, welcome everyone. Welcome. Thanks for coming out on such a cold, cold night. Hopefully nobody slipped getting in. It's very icy out there, so be very careful. My name is Brian Jackson. Most of you know me. I teach physics and astronomy here at Boise State. I'm the host of the First Friday Astronomy event. That's where you are. You're here at First Friday Astronomy. Those of you online, hopefully you can hear us. You may not be able to see us tonight. We're having some issues with the presentation, but hopefully you're able to hear us. So for those of you who never attended a First Friday Astronomy event, welcome. These are a monthly astronomy lecture series. They take place first Friday of every month, 7:30 p.m. year-round. Even if the school is on holiday, we are still here. So we're gonna host this on the next one is on January 6th. Even though the school is officially on holiday, we'll have that event here. We're actually going to be in the education building. We used to be there. Those of you who have attended for a while, we used to be in the education building. That lecture hall is open again. At least I'm told it is. So we'll be back over there. 112. Yeah, that's 112. Yeah, exactly. So we'll be back across the plaza hopefully next semester. That's the plan anyway. We've got some neat talks lined up for you next semester, but I'm going to wait to share them with you until later in the holiday season because we're still finalizing some of them. So look for some emails. You'll get information about the upcoming season, but always on the first Friday of the month, 7:30 p.m. If you aren't able to come in person, you're welcome to join us on the live stream. So this is being live streamed right now on YouTube, boi.st/astrobroncos live. Hopefully you can see that in the back. This is a YouTube channel where you can actually see not only the live stream from tonight, but recordings of previous talks. So if there's something you missed and you want to catch up on it, it should be up there. Make sure if it's not working, let me know that if it's not working. Perfect. Yeah, there you go. This is entirely donation supported. The university does not pay for this. We do not get state funds for this. These events, the money we use to bring our speakers out, pay for our a little bit of students. All of that is donation supported. So if you're interested to help support this program, boi.st/give-to-astronomy. That's where you can go and make a donation. So, and let's see, where did Ben go? Do you want to make an announcement? Awesome.
Unfortunately, you guys have to hear another plug for the Julius Checker Planetarium. So my name's Benjamin Satterwhite. I'm the director of the Julius Checker Planetarium out of Capitol High School. We used to be the TC Bird Planetarium. Some of you guys may remember the original director, Tom Campbell, used to provide a community show called The Star of Bethlehem. It sounds religious. It's not that bad, I promise you. It's more about kind of the mysteries of ancient astronomy. We'll talk about stargazing for December, some cool stuff you guys can see. It should be a nice one for kids and adults. We're going to be doing a double header. We're going to do a 6:30 and a 7:30 show on both December 15th and December 16th. Didn't write it all down here because you're going to have to get tickets this go round. We're expecting a fair amount of folks, but the tickets are still free. And we can seat about 45 in the planetarium. So we don't have a snazzy. I gotta get some sweet websites like that. Ours is like a Google site, so it's like Google site, Boise Schools, Julius Checker. But if you search Julius Checker Planetarium and hopefully or go to Capitol's website, you might be able to find it. Although it does sound like it can be difficult. But if you search this, we should come up. Should be able to get some free tickets. We'd love to have you guys come out. Happy to be a supporter of First Fridays and part of the community. So, did you have a question? Seems reasonable. Yeah, understandable. So I didn't want to write the full website out here because it's quite long. But if you just search Julius Checker Planetarium from a search bar of your choice, or go to the Capitol High School website, you'll be able to find our website there. And we should have a free tickets icon, and you just reserve your seats for that night. 6:30 or 7:30 should be good to go. So thank you so much.
Okay, great. Yeah, that should be a lot of fun. Okay, let me introduce tonight's speaker. You're really in for a treat. We have tonight we have Dr. Angela Dapremont. Dr. Dapremont is got an undergraduate degree in geology from the College of Charleston, a PhD in the Earth and Atmospheric Sciences program at Georgia Tech. And she's currently a postdoctoral fellow at the Johns Hopkins Applied Physics Lab. APL is the lead laboratory for the Dragonfly mission. I think you've heard about that, Dragonfly, a little bit. It's the lead laboratory for DART. If you heard about the NASA's mission to crash a spacecraft into an asteroid, that's DART. It's led out of APL. But tonight we're going to hear a little bit about Dr. Dapremont's research on Martian volcanism. And with that, let's welcome our guest speaker, Dr. Angela Dapremont. Welcome to put this on your lapel or just hold it, whatever.
Okay, thanks for the introduction, Brian. Hopefully everyone in the room and online can hear me okay. So as the title implies, I'm going to talk about mud volcanism specific to Mars. And so much of what we know about this geologic process called mud volcanism is sourced from our knowledge of it on Earth. But there are some important things to sort of keep in mind regarding mud volcanism on Earth versus Mars. And so there are likely differences in how this geologic process operates. So oftentimes another term that's used to describe these proposed mud volcanoes on Mars is subsurface sediment mobilization. So I'll probably use subsurface sediment mobilization and mud volcanism interchangeably throughout the talk. And so on this volume, yeah, is this better? Is this better? Okay, great. Okay, I'll try to keep the mic really close to my mouth. Okay. Okay. Yeah. Okay. I'm gonna keep going while Brian works on that. Okay, so on this title slide, you can see a nice global topographic map of Mars where you have the red and the orange representing high elevation regions, and then the purple and the blue low elevation. And so the black squares over top the global topography map is all the locations where previous researchers have suggested mud volcanoes to be present on the surface. So I like this to start off with this sort of global view because you can see that these proposed mud volcanism sites aren't exclusive to one particular location. They're really found all over the planet, from those high elevation southern highlands, the equatorial regions, and then those lower elevation northern lowlands. So I guess you could think about it on Mars. I'll talk about some of the formation mechanisms, provide some details on that. But I mean, the muddy sediments are essentially just water-rich sediments. So there are proposed sites near the polar caps, maybe some of them at the higher latitudes. But yeah, think about it pretty much just some kind of liquid water, really, in the context of Mars. Yes. Yeah, H2O. Yeah.
Let me encourage you to hold your questions to the end because we've got folks online. They can't hear what you're saying, so they just hear one half of the conversation. Let me ask you this.
Yeah. Okay. No, it's fine. And so, okay, so if we start off then with a definition of your sort of Earth-based mud volcanism, essentially this geologic phenomenon where you have this fluid-rich fine-grained sediments moving from the subsurface to the surface and creating these cone-like features, these volcanoes. And so if we take a look at what can be considered the main mud volcano clusters on Earth, you can see the wide distribution of those as well. And so on Earth, we study mud volcanoes using a variety of processes. So today I'm going to focus on orbital remote sensing in the context of Earth and Mars, but on Earth, other sort of other study methods include seafloor mapping and core sampling. And in terms of geologic setting on Earth, mud volcanoes are typically associated with compressional tectonic regimes. So places where you have lots of tectonic activity, sedimentary basins, and then delta regions, so lots of water as well. And we find them in onshore and offshore locations. Now, from a compositional perspective, which is also the sort of other focus of this presentation tonight, the minerals that are associated with mud volcanoes are those that you would expect from water-rock interaction. So these include phyllosilicates or clays, sulfates or salts, and then carbonates as well. Okay, and so one of the main sites for the study of mud volcanism on Earth is in Azerbaijan. And so we can sort of virtually travel there now. Hopefully the video is working for folks online too. And so we can take a look at what some examples of these sort of idealized mud volcanoes on Earth look like. And so here is one. You can see the size dimensions there, so they're pretty large. This particular mud volcano has what could maybe be considered some erosional rill-like features on its flanks, but you can still see the flows there. And then this plateau-like central crater at its summit. And so when I talk about mud volcanism, as we could see from the map of the main mud volcano clusters, you have all these different formation environments in which they could form. So it's hard to, providing a classification scheme can be kind of difficult. So it's useful then to think in terms of end members. So from a morphological perspective, a feature such as this can have a cone-shaped morphology. So think of that as one morphological end member for mud volcanoes on Earth. And then because there are so many in this particular region, you can travel elsewhere in Azerbaijan to take a look at another example. And so if we land on this particular feature here, again, you can see the flows and then the sort of crater-like feature at the summit. And so this one also has size dimensions really similar to the other example that I just showed, but actually its morphology can be considered pie-shaped. So think about that as another end member. In this region, they might be. It's possible. It's possible. It's possible. Okay, and so now we can take a look at some proposed mud volcanoes on Mars then. So if we start in a region known as Chrysoplanitia, we can see this pretty large proposed mud volcano. You have some, the associated flows could maybe be considered sort of elevated compared to the surrounding terrain. They're a little bit, it's kind of difficult to see. I have some other examples where it's a little more differentiated, but this one is a nice example because you have this really bright crater rim and then the dark material on the flanks of the feature. And then if we move further east in a region called Asdalia Planitia, you can see again these really bright circular landforms. These have smooth flows that are much more distinctive from the surrounding rough terrain. And then there's a final example in a region called Hephaestus Phasae. So I'm going to talk about that in detail as sort of the first of 3 orbital remote sensing studies. But here's just an example of a linear chain of what are called these pitted cones, but they have been proposed to be mud volcanoes. Okay, so now back to formation mechanisms. So again, with classification, it's useful to think in terms of end members, kind of the same thing with the proposed formation mechanisms. So these are 2 examples of proposed formation mechanisms for mud volcanoes on Mars based on our knowledge of them on Earth. So image A is this rapid sedimentation scenario. So sort of going back to the delta regions or the sedimentary basins that I mentioned, imagine sort of a bunch of water-rich, muddy material being quickly deposited into this sort of low elevation basin. And then those materials get pressurized and then extruded to the surface to build these like triangle features that you can see in image A. And then on the other sort of end of the spectrum is this tectonic activity. And so here in image C, this is sort of an example where you have these muddy materials and fluids. They can exploit those faults and then move to the surface and again build these cone features. And then also up front, I like to talk about why it's even important to study mud volcanoes on Mars using these orbital remote sensing data sets that I'm going to talk about. And so if we again go back to what we know about them on Earth, microbial activity has been documented at both onshore and offshore mud volcanism sites on Earth. And so these locations are really unique because they offer insights into microbial colony activity, particularly where you have fluid and methane seepage. And so this is an image of a dark brown microbial colony that's growing in a pool where fluids seep. And then thinking sort of beyond that smaller scale in the context of climate as well, on Earth, mud volcanoes have been suggested to be a significant source of atmospheric methane, and this activity may have influenced atmospheric evolution through geologic time. So then if we extend what we know to Mars, the reason why they're so important to examine is because these proposed mud volcanism sites are key locations of astrobiological interest, and they really provide a unique opportunity to study sediments buried beneath the surface that have been that are now exposed at the surface, so we wouldn't otherwise have access to them. And these sediments could represent life in the deep biosphere of Mars. Okay, so I mentioned that region called Hephaestus Fossae. So here we are again with this global topographic view, but it's sort of centered on the fossae, and I'll zoom in a moment. But just for some sort of geographic context, the big sort of volcano that you see there, that's the Elysium Mons volcanic province. To the south is Gale Crater, where the Curiosity rover is, and then to the west is Isidis Basin, where the Perseverance rover is. And so if we zoom in, again, hopefully everyone can see the video okay. This topographic view is one nice example of how you can see the fossae, what are essentially these cracks in the surface. And they're sort of intriguing for scientific study because they have the cracks themselves have a variety of proposed formation mechanisms. So these include karst-related processes, so think limestone, fluvial activity, tectonic activity, or fluvial and tectonic activity working together. And so this is sort of another close-up view of our specific study region. So this is the first of 3 of the orbital remote sensing studies that I'm going to talk about. And so what you're looking at here, the cutout is from the context camera. So we define that as our context camera, our CTX mosaic. And then the actual image itself this is a thermal nighttime infrared image. And so this does a nice job, again, of showing the cracks in the surface. And then in the upper right-hand corner, I left the that global topographic map for geographic context. So the white box is the CTX mosaic region. And part of the reason we were interested in the fossae themselves is because you have these pitted cones that have been proposed to be due to mud volcanism, but also igneous volcanism. So again, think about those are 2 ends of a formation scenario spectrum. And so what you're looking at here are images from the high resolution imaging science experiment camera. That's the HiRISE camera. So this slide is really just meant to show the variety of morphologic characteristics and image characteristics of these pitted cones in the Hephaestus Fossae region. So that people use a technique called crater counting for to try to put age estimates. That's sort of outside of my expertise. I actually cannot remember if a specific study has been done in the Hephaestus Fossae region for crater counting, but there are geologic maps from the USGS that can give you age information. Yeah. And so, okay, so the color boxes on the CTX mosaic correspond to the variety of orbital remote sensing data sets that we use to try to study the pitted cones. So we got elevation data, topographic data from digital terrain models from CTX, also from HiRISE. And then we were interested in compositional information from the CRISM instrument, particularly using visible and near infrared spectroscopy. So we were essentially looking at how light interacts with materials on the surface, and that can tell us something about what they're made of. And so when we were going through the CTX data, looking at the study region, we found some interesting observations associated with the relationship between the cones and the fossae. So this is just an example of some of what we found as denoted by the yellow arrow showing the relationship there. And then I showed the previous slide with the HiRISE images of some of the variety of morphologic characteristics, but sort of getting more specific. So here, the white arrows on each of these HiRISE images is meant to show some of the more common characteristics of the pitted cones, particularly these smooth flanks. But then on the image on the left, you have this pink arrow, which we classified as having this pitted cone as having a more degraded crater rim. And that's very different from what the green arrow is pointing out, where you have a pitted cone with a sharper, more well-defined, maybe even younger crater rim. Okay, so here's an example of the visible and near infrared spectroscopy data we used. So on the far left is a CRISM targeted data image, and the blue box is outlining the cone that you can see the HiRISE color image of that's adjacent to that targeted image. The blue spectrum here was informative because we identified an absorption feature in the 1 micron region. Each of these spectral plots that I'm going to show, you'll see some more examples later. They're going to have wavelength on the x-axis and then essentially reflectance on the y-axis. So here, this particular PRISM signature was most consistent with magnesium olivine. So that's trending toward an igneous formation scenario, so away from that mud volcanism formation scenario, because when we get these data from the Martian surface, like you see in the blue spectrum, we have to have something to compare them with to make the proper, a proper mineral identification. So the reference spectrum is the magnesium olivine there in the black. Okay, so here's an example of the morphometry data we were interested in. So looking at the size distribution of the features. I'm going to start with the image on the right, which is a HiRISE DTM. And so that black dot, we defined the center of each of the pitted cones. And then we were interested in the crater width as well as the cone width. So the widest circle is the cone width. And then those black lines that you see are the directional profiles that we use to get average topographic information for the cones. And so the image on the left is showing an example of the topographic profiles and then how we were able to use those to get the morphometric data that we were interested in. And then I'm not going to spend too much time on this slide because it's a lot of text and numbers, but the main takeaway is the fact that when we got the size distribution data for the fossae pitted cones, and then we compared them with igneous and mud features on Earth and Mars, we found the most similarities with these features called rootless cones, where you have lava and ice or water interacting, and it creates this explosive scenario. So it's volcanism that isn't connected to a vent, like a root, and then mud volcanoes as well on Earth and Mars. So when we were doing our morphometry analysis, we sort of realized that you can't necessarily look at it in a singular way. It was really important to take a look at the morphometry and the morphology together. So the image set on the left is showing a pitted cone in Hephaestus fossae. And you can see it has some similar characteristics as a proposed mud volcano in that Chrysoplanitia region that I mentioned. Now, those are kind of different from the image set on the right, which is from the CTX camera. The one on the left is from the HiRISE camera. So the image set on the right is showing one Hephaestus fossae pitted cone, and then these pitted cones in that Isidis Basin region. So that's west of the Hephaestus fossae region. So you can see they look pretty similar, much also very similar. But then when you, so if I put the formation scenarios on top, But then when you add in the morphometry data with these sort of morphology image characteristics, it starts to tell a little bit of a different story. So with the image set on the left from the high-rise camera, that proposed mud volcano in Chryse Planitia is much larger than the one in Hephaestus Fossae, whereas the morphometry and the morphology match a little bit better between the Hephaestus Fossae feature and the one in Isidis Basin. And so our final technique that I'm going to run through really quickly was spatial analysis. So we essentially mapped close to 1,000 cones in that CTX mosaic study region. And we were trying to use this tool to see if we could assign a formation scenario to the pitted cones. And we weren't actually really able to do that, but we were able to get some formation environment insights, particularly the fact that some non-random process was controlling cone distribution and individual cones formed near pre-existing cones. So then if we take a look at the conclusions then using our different data sets from this sort of first orbital remote sensing study, the strongest line of evidence actually for an igneous formation scenario was from the composition, the visible near infrared spectroscopy. The morphometry, the Hephaestus Fossae cones just showed similarities with igneous and mud features. So again, that wasn't necessarily definitive, and neither was the spatial analysis information either. But once we were done with the Hephaestus Fossae study, because part of what we were interested in was the compositional information, we sort of became curious about elsewhere on Mars, where you have these proposed mud volcanoes beyond Hephaestus Fossae, what might their compositional characteristics be? Particularly because at the time, there had been maybe a few studies, two-ish, that had used the CRISM data to take a look at compositional characteristics of proposed mud volcanoes to try to tell should the expectation be similar or different given what we know about their mineralogies on Earth, but a lot more could be done. So we then this is the second of the 3 orbital remote sensing studies, so what we call the global study using data from the CRISM instrument. And we focused on the 3 broad regions that you see here over top the global topographic map. And we used, so that targeted data that I mentioned, CRISM has 2 detectors, an S detector with the visible data, and then an L detector with the near infrared data. So we essentially used all available CRISM targeted data. And then we use what's called the spectral ratio method. So you essentially draw a square over your compositional region of interest on a CRISM targeted data image, and then you divide it by some spectrally bland, something really boring that's in the targeted image to try to bring out your signature and then reduce noise in the CRISM data set. So if we start in the Mars Canyon system, Valles Marineris, so these are some high resolution images of some proposed subsurface sediment mobilization features. And they have been previously classified as knobs or rounded knobs, which is just another term for proposed mud volcanoes that have been used to describe them. And if we take a look at their compositional characteristics, so again, we have in each of these spectral plots, wavelength on the x-axis and reflectance on the y-axis. Here, we were able to identify these pretty consistent 1.4 and 1.9 micron water absorption. So you can see those indicated by the dashed lines. And that was essentially just telling us that there's hydrated minerals, there's water in the mineral structure associated with these proposed mud volcanoes. Now, I should also mention that the color boxes correspond with the spectra in the plots, and it'll be like that on subsequent slides as well. And so the purple spectrum was particularly interesting because we were able to go sort of one step beyond the identification of hydrated minerals. So in addition to that 1.4 and 1.9 absorptions, we also identified a 2.23 micron absorption. So that's the third dashed line there. And that was telling us that maybe there was some unaltered hydrated volcanic glass associated with the proposed mud volcano in this region. And then elsewhere in the canyon system, you have these features called clastic pipes, and they're essentially grouped with mud volcanoes in the study of subsurface sediment mobilization on Mars, because they have a very similar formation mechanism. And so here we have some high resolution images of these. And then again, these a pretty consistent 1.9 micron water absorption that's indicated by the dashed line here. So just more evidence for hydrated minerals. And there are a final set of these really distinctive, these really kind of weird, dark features that have also been proposed mud volcanoes. Those are also called knobs by a previous researcher. But interestingly, their spectral signatures veered us away from the mud volcanism scenario, because we identified high calcium pyroxene associated with these proposed mud volcanoes actually on Mars. Okay, and then if we move further into the Southern Highlands in this region called Terra Serenum, you can see another high resolution image of a proposed mud mound. And so here it was similar as in Valles Marineris, so you have the consistent 1.9 micron water absorption. So you can see the dashed line again there. And then finally in Arabia Terra, this is a CTX image of a proposed mud mound. And this particular spectrum was really interesting because we found 1.9, 2.1, and 2.4 micron absorption. So those 2 micron region absorptions are indicated by the dashed lines here. And going back to what we know about mud volcanoes on Earth, one of the minerals we were looking for were sulfates. And so we kind of got excited because we thought, well, maybe there's some sort of sulfate mixture associated with this proposed mud volcano. So we could say, yeah, there are some similar minerals on Mars, but we had to sort of be cautious because in the Chrism infrared region that's shown on the x-axis, you have noise artifacts, so essentially false absorptions at some of these same positions as the dashed lines. So we sort of had to be a little more cautious in our interpretation here. But there were proposed mud volcanoes elsewhere in Arabia Terra that had those 1.4 and 1.9 micron water absorption. So again, indicating the presence of hydrated minerals. Okay, and so these are the overall conclusions from this second study. Again, I know it's a lot of text, but there were 2 of them that were particularly informative for leading us to the third study I'm going to talk about. So we're coming up on 3 of 3 orbital remote sensing studies. And so when we looked across those 3 broad regions using the Chrism data, we were really only able to say, okay, there are hydrated minerals present associated with these proposed mud volcanoes. But we really wanted to get more specific than that and see if there were any orbital remote sensing tools available that could allow us to make confident identifications of the minerals that we know comprise mud volcanism units on Earth. So as I mentioned, those clays and carbonates and sulfates, these things indicating water rock interaction. And so much of what I showed for the high-rise data, those images that I showed, those can be thought of as sort of the qualitative observations of the high-rise camera, but it also has these really underutilized quantitative capabilities. So then we decided to use what are called these color band ratios, these quantitative color band ratios from the high-rise camera to try to get some more mineralogical information. Now, there are a series of previous studies that have incorporated this, this type of high-rise data into their analysis of the compositional units on Mars. But similar to how I showed the Chrism data from the Martian surface and then the reference spectra, there was really a lack of knowledge about how well the high-rise color band ratio data from the Martian surface might match reference spectra, these lab materials, these reference spectra, which I'll refer to them as. So that was part of our motivation for this study as well. Okay, and so for this third orbital remote sensing study, we focused on the 3 broad regions where the Chrism data revealed the presence of hydrated minerals. And so I'm just going to quickly go through the methods because the color data plots themselves are actually more fun and interesting to look at. So we use the high-rise color products. We drew our ROI, so our regions of interest in this case, over top our mud materials on a high-rise color image, and then some select surrounding units. So particularly we were interested in the surrounding materials that exhibited color contrast. So I'll show you some examples of that in the subsequent slides. And then we got the reflectance values using the equation on the slide. And so high-rise has these three bands, IR and the IR red and VG, essentially in the visible portion of the electromagnetic spectrum. And so we were interested in the ratios that you see here, the IR red and the VG red. And then we were able to gather those data from the Martian surface and then compare them with reference materials. Okay. So here's an example of the color distribution associated with the proposed mud volcanoes in Valles Marineris. So each of the color plots that I'm going to show is going to have the IR red ratio on the y-axis and the BG red ratio on the x-axis. And so, okay, here's an example of a proposed mud flow. And some of the select surrounding materials that we were interested in. So you can see the blue color contrasting with the white proposed mud materials. And then here's an example of what's probably my favorite high-rise color image of these proposed mud volcanoes, particularly because you have you can see the color distribution associated with them. So you have these tan materials, these white and light blue materials, and the white materials. And here's another final example where you have this sort of gray flank material. Now, these are the reference materials that we were interested in comparing with. And so they were sourced from the US Geological Survey Spectral Library, and then these additional reference vectors. So the CRISM instrument has its own spectral library. And so you can see that some of the white and light blue and the tan mud materials plotted up near this clay mineral nontronite from the USGS Spectral Library, and then jarosite, which is a sulfate also from the USGS Spectral Library. The blue materials plotted up near these pyroxenes, so these igneous minerals, and then the gray was plotting down near the olivine mineral phthalite. And so another sort of data visualization tool was looking at the averages of the point clusters and then plotting them in this ferric versus ferrous reference mineral divide. And so we did this because going back to what we know about the proposed, or going back to what we know about mud volcanoes on Earth, this divide could sort of help us understand if there were minerals associated with water rock interaction associated with the proposed mud materials, and also taking a look at the surrounding units. So when we applied that reference mineral divide, we found that when you're looking at the colors, there was a sort of interesting observation where you have the tan and yellow and white mud materials were often plotting on the ferric side. So think the sort of alteration side indicating water rock interaction, whereas the blue, those darker blue non-mud materials plotting on the ferrous side. So lack of alteration essentially. And then we did the same thing in Terra Serenum. So this is the color distribution associated with the proposed mud volcanoes and surroundings there. And then, so here's some examples of some close-up views of what the color distributions look like, and then where we were able to gather the data from. And so Terra Serenum was particularly interesting because it was actually a rare case where you have point clusters plotting directly over top a reference mineral, particularly nontronite from the CRISM Spectral Library. And so again, it opened the door to this question, which is still an outstanding question, particularly because we pursued these methods to try to take a look at the high-rise color data as a complementary mineralogical investigation tool to other data sets like CRISM. So it introduced this question then of, are there clay-rich muds associated with proposed mud volcanoes in this region? So that's just, yeah, an example there. And then when we applied the ferric-ferrous divide, it was a similar sort of story as in Valles Marineris. So you have the tan and the yellow mud materials often plotting ferric versus the blue non-mud materials often plotting ferrous. And then we did the same thing in Arabia Terra. So we didn't observe as much color distribution because we were really only able to make use of one image in this region. But again, it was still interesting enough. And so a similar sort of ferric-ferrous reference mineral divide story there as well. And so then I'm just going to go through the overall conclusions then from this third orbital remote sensing study. So when we looked at the high-rise reflectance plots across the three broad regions, we found this commonality where you have the tan, yellow, and white mud materials, so materials of sort of common specific colors, often plotting on the ferric side, that sort of iron alteration side of the divide, versus the blue non-mud surrounding materials were often plotting ferrous. Now, the examples that I showed are ones where you could see a clear divide, but that wasn't always the case. It wasn't always evident in every single reflectance plot. And that's probably because most of what we're looking at, if not all of what we're looking at on the Martian surface, is mixtures of different materials. So things that are not compositionally pure, made up of one single mineral. And then we did observe a limited range in that IR red, BG red space among the three regions. So I'll talk about why that's important in a few slides. And then again, in Terra Serenum, this question of, which is still outstanding, are there clay-rich muds associated with proposed mud volcanoes in this area, which would be really important in the context of comparative planetology. And in the overall region, sort of the surrounding region where these mud volcanoes are, lots of secondary alteration minerals indicating water-rock interaction have been found, have been identified using the CRISM data. And so if there were clay-rich muds, it wouldn't necessarily be surprising. And then going back to that limited range. So dust is everywhere on the Martian surface. So we have to take that into account, particularly in orbital remote sensing data and observations and conclusions. And so there was a previous study that observed, in terms of the BG red ratio, a similar value that we did. And they attributed this to an overall ferric signature. So essentially they attribute it to dust contamination on top or within surface material. So we had to acknowledge that, and their findings were certainly relevant to our observations as well. And so when we try to sort of take a look back then, or take a step back, putting all three studies together to try to answer this question that you see on the slide, we could pretty much say, okay, across Mars, these proposed mud volcanoes exhibit pretty consistent hydrated minerals. In some cases, a limited number of cases, we're able to make specific identifications, like the volcanic glass and the high calcium pyroxene. And then again, this question of the clays in Terra Serenum. And in the Hephaestus phosphate region, if we add that one in as well, the compositional information was actually veering us away from a proposed mud volcanism hypothesis. And so mud volcanoes are also particularly intriguing and relevant to this topic of land use policy on Mars. So this also made up a significant contribution of my PhD research, in addition to the orbital remote sensing studies. And so by land use policy, what I mean by that is an example of what you can see here. So this is a Mars settlement envisioned by SpaceX. And, you know, given the sort of lofty goals of these private space companies like SpaceX and Blue Origin, and then also the goals of space agencies around the world, so some of which are more well-established, like NASA, versus you have lots of countries and nations establishing, they're sort of newer players in space exploration and establishing their own space agencies for the first time. It's important to think ahead about some of these issues that will be raised by eventual human activity on Mars, and sort of thinking about science and human activity together. And so related to mud volcanism and the orbital remote sensing data studies that I discussed, you have these questions then, like, these proposed mud volcanoes definitely have astrobiological potential. So would they need to be environmentally protected in a properly applied land use policy? Or how might human inhabitants of Mars be allowed to interact with these proposed mud volcanism sites if they wanted to do scientific investigation? So I enjoy thinking about some of this as part of my PhD. The paper has been published in the journal Space Policy. So here's the title if you're interested in more about that. And let's see. So I think that, yeah, that's my last slide. So thanks so much for taking the time to listen today. I wouldn't have been able to do that without the funding agencies that you see here, and really the people that are also listed on the slide. And thank you to Brian for this opportunity to speak about mud volcanism on Mars. So I'll take any questions now.
To take questions, I'm going to ask people questions.
So, yeah, so the mud volcanoes will usually be sort of topographically elevated compared to the surrounding materials versus the compact activity. Well, they have a compositional difference, at least that we were able to show. Maybe for, if I'm understanding your question correctly, maybe for a chemical difference that might require like a in situ study, so a rover using a Oh, I'm sorry, I'm so sorry. Say it again, sorry. Possibly. But yeah, I think something like that to provide a more definitive answer would require like a human going up to it, or a rover going up to it and using some instrumentation to look at chemistry. So, well, most of the proposed mud volcanoes, I mean, what I showed there in the, oh, I should repeat the question. Sorry. It was about, related to mud volcanoes and their source and the polar cap. So have that correct. So there haven't really been very many, proposed to be that high in latitude, maybe 3, I'm looking at the map, maybe 3 locations, one of which would be closest to the pole. So I feel like in the context of understanding that relationship, that someone could maybe do a study of that one particular region, but it's not necessarily common. Right. Mm-hmm. Yeah, well, I guess so far we've only really been able to identify water associated with the proposed mud volcanoes. Yeah.
Question online here. We got a couple of questions online here. So let's see. One person asks, how did you get into mud volcanism? Did you stumble into it or actively go into it for that as a research project?
Yes, I very much stumbled, fell on my face into it. So let's see, can people hear me okay still? At the beginning of my PhD, I was interested in that Elysium Hephaestus Fossae region. And then looking at the orbital remote sensing data there were these pitted cones. And then if you read, one paper after another, it's like, oh, they've been proposed to be mud volcanoes. And there are only a few papers on mud volcanoes. And I'm really desperate for a dissertation topic. So why don't I look at these mud volcanoes? So yeah, just sort of one step at a time fell into it.
Other questions in the back there?
Well, oh yes, thank you for reminding me. So the question was about sort of traditional igneous volcanism and temperature and mud. So on Earth, these sediment, that's another term, sedimentary volcanoes, these mud volcanoes usually have a much lower temperature profile compared to the igneous volcanoes. There have been lab studies done that I can think of that sort of get you closest to temperature characteristics of Martian mud volcanism, because these experiments looked at mud flows in a chamber simulating Martian, I think, atmospheric pressure and maybe one other characteristic. So that is sort of like a first step for understanding the temperature profile, temperature characteristics of Martian mud volcanism, but that's sort of as far as it's gone, at least that I'm aware of.
Well, let me get another question online. I'm going to try to go back and forth between the two rooms. Let's see. How do you think the subsurface pressures are generated to drive the Martian volcanism?
So, you want me to repeat that one, or since you said it? Okay, thanks. So again, going back to what we know about mud volcanism on Earth, so you have a variety of, I know it's sort of vague, but it really is such a wide distribution, and we're still understanding it for Mars and what might be realistic for Mars. So a variety of types of pressurization mechanisms are associated with Earth mud volcanism. So you can have mineral dehydration, literally just compacting sediments so much that they extrude the mud. What are some other ones? Associated with methane and other sort of hydrocarbons and gases and whatnot. So those are just some examples. There's a lot of literature. Well, there's a significant enough amount of literature on mud volcano formation and pressurization mechanisms on Earth. So looking up some of those papers could be maybe helpful. So the question was, for the mud volcanoes on Mars, do they explode like the ones on Earth, or are they more sort of gentle and effusive? So the latter, yeah. So they're more, at least the ones that have been studied so far, a explosive scenario isn't really typical, I would say. Yeah, think of it more as just building up these flows over time.
Hear me online, folks? Okay, there we go. Perfect. Yeah, so another question. Any age estimates of the volcanoes or flows?
Yes. So let's see. I think I mentioned maybe at some point during the talk yeah, it died because I think it sucked the power. The presentation ran the power on my laptop. That's okay. Yeah, so the sort of best information for the age estimates is going to come from some of those USGS, the geologic maps, because these features are so small. Trying to do crater counting on a small area would essentially be really challenging. I mean, but if someone else is looking for a dissertation topic or a research topic, maybe you could explore that. Oh.
Great. Yeah, question here.
Yeah, so for the high-rise color data, the quantitative ratios, the high-rise camera can take what are called stereo hairs and essentially other types of repeat path observations where you're looking at the same area but with different geometry characteristics. And so I didn't get a chance to talk about it in detail today, but we have done some analysis where, so all of the color data plots that I showed those are from one image, but then if you have a repeat observation, they can shift, and then that could influence your interpretations. And sorry, the question was about orbital remote sensing images and repeated observations and how that could change interpretations. Well, so far, so we're definitely still working through this. So far, let's see. So from some examples I can think of, what was interesting was in Valles Marineris, we observed more shift in the point clusters compared to Terra Serenum. And so, it could tell us something. I mean, it could have to do with the color variation and distribution in the images, but it varies. So every single image set that we looked at, it didn't necessarily change the interpretation every single time, but it could. Mm-hmm.
Let's see. Yeah, Brian.
Yeah, so
Sorry.
So the question was about if the mud volcanoes on Mars are indeed more effusive, why do they have those central craters? So that can vary by location, because some of what I showed also have the mounds, right? They don't necessarily have the pits. But in the case of that really nice one in Chrysoplanitia, you can have the mud materials building up around a vent. And part of my dissertation, we also did a little bit of modeling, trying to understand that. Where does the central crater come from? And we sort of we got kind of far, but that is sort of an outstanding question that one could look at.
PhD right there, right?
Yeah. Yes.
Yeah,
So,
go ahead, Benjamin.
Yes. So, yeah, I mean, I feel like, sorry. So the question was a policy related question, given that you have Antarctica as a model for land use policy on Earth, and you have the private companies and space agencies, how does all that work, I guess? So yeah, that's something that's definitely ongoing. I mean, I would argue the most recent example of getting to some sort of standardization would be the Artemis Accords. I think, I can't remember when exactly they came out, but those are maybe fairly recent. It's talking about the US being a leader in space exploration and the peaceful purposes, peaceful uses of outer space and land on the moon and on Mars. So I think it's something that's still being worked through. This sort of private company government agency, who owns what, if you have waste from human activity or parts from a rover, who can take that and use it. Yeah, so these are interesting policy questions that are still ongoing. Yeah.
There's another question in the back here. Yeah, go ahead.
Yeah, so the question was about the presence of olivine on Mars and their association with the mud volcanoes. So I mean, the compositional distribution of olivine, I just showed a few examples that were in our reference library. There's a wide compositional distribution. And so, but in terms of thinking about astrobiological potential, we were really more interested in the alteration stuff. So yeah, I guess in terms of olivine and where you might find life, I mean, it's in the context of the proposed mud volcanoes that sort of veered us away from maybe where to look. But I'm sure there's lots of literature about more specifics about olivine and its role in sort of astrobiology.
Let's see. Yeah, in the front.
For me, probably not a lot. This is why I'm so ready to sort of pass it on. The question was about what's next in mud volcano research on Mars. So the reason I say that is because today I talked about the CRISM data and the HiRISE data, right, for compositional information. There's also an instrument from the ESA, the European Space Agency, called CASIS. And so that has essentially one more band. So instead of the 3 bands from HiRISE, you have 4 bands further into the infrared. And you can use those data for compositional information. We've tried with to use the CASIS data to look at the proposed mud volcanoes, and we haven't really. You can apply different corrections to try to essentially improve the signal, the information you're getting from the surface, but we haven't really gotten very far. So again, if someone is interested in using CASIS data, yeah.
Second PhD right there.
Yeah, second PhD, exactly.
Yeah, please.
Yes, yes. Yeah. So what the question was about the mud volcanoes. We're assuming they're dormant, right? So they're not active. And so what we're looking at on the surface. So what we're looking on the surface right now is this is what is currently exposed. But as you mentioned, so there are other examples of these repeat pass observations with the HiRISE camera where maybe you could see an impact, right? Or if you guys have maybe heard of the RSL, recurring slope lineae. We don't, at least to the best of my knowledge, we haven't seen any movement associated with these proposed mud volcanoes, but you can only take a limited number of repeat pass observations anyways with the HiRISE camera. So yeah, did I answer your question? So the question was, what do we look at it as the past or what could happen in the future? So we're looking at it as what we see on the surface today is telling us about what happened in the past. No, not right now.
That'd be cool. Yeah, Leaf.
Hydrated minerals. Yeah, so the earth associated compositional stuff that I talked about, so the clays and the sulfates and the carbonates. So essentially by hydrated minerals, I mean these are minerals that have water in their structure. So it's telling us something about water rock interaction, and then sort of thinking broad horizon goal. If we can identify those kinds of places, even beyond proposed mud volcanism sites, then this is where we might want to send a rover. This is where we might want to send humans, because it's some place where there could have been life at one point. That's very broadly speaking.
Yeah, the mineral grains can capture water molecules like little cages, and so there'll be a hydrated mineral. Does hematite have water in it?
Hematite is a alteration mineral. Let's see, in the infrared, it doesn't have a 1.9 micron absorption, but I think it has interesting 3 micron absorption. Right. Okay, thank you.
Any last questions? Yeah, thanks, Leif. Okay, well, let's give Dr. Dapremont another round of applause. And join us again in January. We're going to have Jared Hand, who is a cosmologist, a supernova cosmologist at the University of Pittsburgh, is going to join us. Yeah, it should be a lot of fun. Have a good night. Stay warm.